Okay, good evening, everybody. And welcome to the Lifestyle Organic Chemistry session for the Spring 2014 semester. You like that, eh? Okay. In today's session, we are going to finish up on chapter 24. Okay, but before we start the discussion on chapter 24, just a couple of announcements. I want to remind you that the exam number 4 is scheduled for this coming Thursday. That is April 24. And also for the graduating seniors, your final exam is tomorrow. That is Wednesday, April 23rd at 6 p.m. That will be in room G8 of the chemistry building. Okay, also a reminder that the final exam is scheduled for next week Thursday. That is May 1st at 6 p.m. and that will be in this room. Yes.
What are we doing extra credit?
Extra credit. There is no extra credit. But there is. Do you mean the
survey?
The survey? Yeah. I was going to get to that. Okay, there will be a couple of surveys. One from the College of Arts and Sciences. I believe if you go to their website, you should be able to access the survey for my class. So make sure you do that. And when you complete that survey, send me an email just let me know that you've done it. I think they generally give you a completion, a thank you page or something like that. So send me a copy of the completion page, so I guess we'll give you credit for that, for the completion. And also, there will be another online survey that will be coming from me. Okay, and that I will send to you on Tuesday next week. Okay. Now, the one from the College of Arts and Sciences, the deadline for completion is that will be next week Wednesday. So you make sure that you complete both of them by next week. Yes.
Graduating seniors for the survey.
Yes, you have to do the same survey as everybody else.
Yeah, you said the other one that you're going to send out next week.
Yeah, I'm going to send it to everybody.
Yeah, I know, but our grades are due on Thursday.
Well, that doesn't really matter. That doesn't really matter.
You said you were putting them in Thursday night.
Yeah. Okay. Anyway, so make sure you complete those survey by next week. Okay. Now let us finish up on this chapter 24. Okay. When we left on Tuesday, when we left on Thursday, we were discussing the synthesis of amines. So what we want to do now is just to take off on that particular topic. Okay, after the synthesis, then we are going to go to reactions of amines. And if we have a little bit of time, we might show you some examples of heterocycles. Okay, so let us continue synthesis of amines. I recall when we left on Thursday, I gave you 4 methods already, right? I think the last one I gave you was method number 4. Okay, so let us start with method number 5. I will call that Gabriel synthesis. In the Gabriel synthesis, you start with this molecule here. This is called phthalimide. And because this nitrogen is between two carbonyl groups, this hydrogen here is fairly acidic, so therefore you could use potassium hydroxide, either a potassium hydroxide or sodium hydroxide, in an acid-base reaction. So what do we get? You get potassium phthalimide. There's a non-bonding pair of electrons here. So we get potassium phthalimide. And then this potassium phthalimide will now react as a nucleophile. We are going to alkylate the nucleophilic nitrogen here. So we could use any alkylating agent, and this is an SN2 reaction. Say, for example, we want to use this alkylating agent. Let me change the color of this pen. Okay, as in the case of all SN2 reactions, the alkylating agent, the leaving group, must be attached to what kind of carbon? Primary or secondary, exactly. Okay, so this will be an SN2 reaction. So now we have the alkylated phthalimide. Now you take the alkylated phthalimide, you hydrolyze using potassium hydroxide in water. So you could use hydroxide. In so doing, you are going to generate a primary amine. So this reaction gives you a primary amine. Plus, of course, you have this phthalate as a byproduct. But for the most part, our interest is on the amine product. So if you write this and you do not show the phthalate with this molecule here, that would be fine, just as long as you show the amine. So this reaction here, this sequence of reaction here, you notice here, what it gives you is a primary amine. Okay? Now, how do you normally do this? You don't have to write this out in sequence just as I've done here. You could simply do this. Step 1, hydroxide, and what does that do? You form the nitrogen nucleophile, and then step 2, you introduce the alkylating agent. Keep in mind your alkylating agent must be either a primary alkylating agent or a secondary alkylating agent. Say, for example, we could do this. And then finally, we have the hydroxide to hydrolyze the alkylated phthalimide. And here, therefore, the product will be this here. And this is benzylamine. There is one word. Let me. So this, the Gabriel synthesis is a very good method for making primary amines. Okay, so that was method number 5. Okay, so let us go to method number 6. Well, let me give you another example. Just step 1, step 2. We use iodide. And step 3, hydrolyze to obtain the amine product. And if you like, you may want to include the phthalate, but you don't have to. Okay, and this is your amine product. Okay. Okay, so now let us go to method number 6. Okay, all of you already know this one. Reduction of nitro compounds. Here, for the most part, I will use aromatic nitro compounds. Say if you take a nitrobenzene, for here you could use lithium aluminum hydride followed by dilute acid or water, and that will give you in this case it will give you a primary amine. You could also use iron in dilute acid. You could also use hydrogen with palladium or platinum, or to also use tin chloride in dilute acid. Each one of these reagents here will transform a nitro group to an amino group, in this case a primary amine. Okay. Okay, so that is method number 6. Number 7. Courteous rearrangement. This one is closely related to the Hoffman rearrangement. Huh? Yes, courteous. Now, if you take, say for example, we take this, take an acid chloride, and you react the acid chloride with azide, say sodium azide, the azide is a very powerful nucleophile. So what do we get? We get a nucleophilic acyl substitution reaction in which we get this product here. This is azide. Okay. Structurally, this is actually what it looks like. Okay, so this is acyl azide. And then if you take the acyl azide, you apply heat, you get a rearrangement. They're what we call isocyanate. Okay, in essence, what is happening here, if you look at the azide, let me write the resonance for it. If you take a look at this azide here, write the resonance for this, which you have this here. Now what do we have? Okay, so in essence, what we are going to get is a rearrangement in which, of course, this is positively charged. Now, this part of the molecule here, this is nitrogen. Nitrogen is a very stable molecule, as you guys know already. This is nitrogen, and nitrogen will live very easily. It's a very good living group. So what happens? Nitrogen is living, and when it is living, then creates the opportunity for the acid to shift, and that is how you get your isocyanate. Okay, and of course this will. Okay, so that is how you get your isocyanate. Now, once you get your isocyanate, you obtain the isocyanate. Once you add water to this, it goes through a few more steps, but I will simply just give you the final product. You will end up with this here plus carbon dioxide. In other words, eventually we are going to lose carbon dioxide. What happens here, this water attacks this carbonyl, form what we call a carbamic acid, and that intermediate carbamic acid will lose water. We'll lose carbon dioxide and then form the amine. Okay? So this is what we call the Cotier's rearrangement. So yes. I can hear you. Oh, you mean this here? Are you referring to this structure here? Okay, so what is the question? No, I was just showing you how, okay, I will show you the movement of electrons that result in the formation of the isocyanate. Okay, what happens here, let me take all of this out of the way. What happens here, the nitrogen is living, okay? Nitrogen is a very stable molecule, so it lives very easily, very good living group. And once it is living, therefore this now becomes an electrophilic, become positively charged, and the alkyl group will simply shift to the nitrogen. Okay, while it is doing that, the pair of non-bonding electron here will also now form a bond between this nitrogen and this carbon, and that is how you form the two double bonds. So that I was just simply trying to show you how we go from here to here. Okay? Okay. So anyway, so this is the Cotier's rearrangement. So ordinarily, nobody will ask you to write the reaction mechanism the way I've given you so far. But what we normally ask you to do is to give the product. So if I have this, okay, now you know how we get the acid azide, right? That comes from the acid chloride. Step 1, you heat it up, and then what you get with that, you get the isocyanate. And then step 2, hydrolyze with water, and then you get your nitrogen plus carbon dioxide. Now, what is most important about this reaction, just as in the case of the Hoffman rearrangement, is that it allows you to lose one carbon atom. Okay? So this is what another reagent that allows you to lose a carbon atom. Because if you notice here, We are starting with the starting material here has 4 carbon atoms, and then the final product only has 3 carbon atoms. Okay, so it is similar to the Hoffman rearrangement in that regard. Okay, another example, we simply do this. Okay, just as in the Hoffman rearrangement, this also gives you a primary amine. Okay, sodium azide, step 1, and that will give you the acyl azide, and then you have step 2. You apply heat, and that gives you the isocyanate, and then finally you hydrolyze with water, and that gives you your final product. Now you do not have to include the nitrogen or carbon dioxide in your product. Our interest is only in the amine. Yes. To do what? Yes, yes. This only gives you primary amine. Yes. Now, so far we have been giving you a lot of methods for primary amine. Let us look at methods that will give you both primary and secondary and tertiary amine. Okay, so that was number 6, right?
7.
That was 7? Okay. So 8. What we call reductive amination. I believe we did this before when we discussed aldehydes and ketones. Amination. If you take a ketone or an aldehyde and you react with ammonia, okay, you recall that we got an amine. We got an amine. And then we could take the amine. We could reduce the amine with hydrogen, catalytic hydrogenation, using either palladium or platinum. In this case, we also get a primary amine. We could also reduce the amine with sodium borohydride, followed by water. Okay, the amine could be reduced to a primary amine also. Another reagent that we also could use is sodium cyanoborohydride, step 1, and then step 2. Okay, each one of these reagents will transform the amine to a primary amine. That is when we react the ammonia with either the carbonyl of a ketone or the carbonyl of an aldehyde. Now, supposing we want to obtain a secondary alcohol, a secondary amine.
You said it works for ketone or aldehyde.
Say that again.
You said it works for ketone or
Yeah,
aldehyde.
carbonyl of ketone or aldehyde. Okay, supposing we want to make a secondary amine, in that case, if you start with a ketone or aldehyde, what you want to do is to use a primary amine. Use a primary amine, and that gives us that amine. Amine is a carbon-nitrogen bond.
Can you do H2PD?
Huh?
Can you do H2PD?
Huh?
Can you do H2PD?
Yes, yes. That's what we're going to do now, yes. That is correct. At this point, you now want to reduce it. All of those reagents I gave you that you could use with the earlier reactions, you could also do the same thing here. Hydrogen with platinum or palladium, or sodium borohydride, followed by water, or sodium cyanoborohydride, they all give you, in this case you obtain a secondary amine. So if you want to obtain a secondary amine, this would be a good method to use. Now, supposing you want a tertiary amine. Supposing you want a tertiary amine. In that case, you will react the ketone or aldehyde with a secondary amine. So we could take a secondary amine here. Say we use dimethyl amine. Okay, we say step 1, and then step 2, we could use any one of those. In this part, okay, this is slightly different. Let me give you more information here. Now, in the case of the secondary amine reacting with the carbonyl of a ketone or aldehyde, you do not obtain an amine, you obtain an inamine. We did this when we discussed the chemistry of aldehydes and ketones. So you obtain this, Okay, that is like a vinyl amine in amine, or you may call it vinyl amine. Okay, this part of the molecule here, anytime you have a carbon-carbon double bond, we say we have a vinyl group. Okay, so that is why we refer to this as vinyl amine. So at this point, you could now simply use the same reagent, in this case, hydrogen and platinum. Okay? Okay, in this case only hydrogen and platinum, or hydrogen and palladium. So hydrogenation, not sodium borohydride. So therefore, this allows you to form a tertiary amine. Another example, supposing, let's use an aldehyde for a change. Supposing we have an aldehyde, and then we have this here. N-methyl ethylamine, step 1, and then step 2, step 1 will give us the enamine, and then step 2 we do hydrogenation. And so we get this here. Let me use a different color here. Let's make this. Now we obtain this. Now we obtain a tertiary amine. Okay, so that was number 8, right? Okay. Okay, I'll give you one more method for the synthesis of amine. Nine. SN2 reactions of ammonia and amines. The amines are capable of reacting as nucleophiles. So for example, if I have this here, of course when we say SN2 reaction, you know that we have to use an alkylating agent in which a leaving group is attached to either a primary carbon or a secondary carbon. If you have this, and I have ammonia here, what happens? An SN2 reaction, ammonia comes here, simply attack this carbon here to displace the bromine. So now we have this. And of course the bromine that is displaced is here. So what happens at this point, this bromine we'll simply pick up notice that we are now forming a quaternary ammonium compound. So this bromine comes here to grab this proton, and the proton will leave a pair of electrons with the oxygen. So now you have this here. So it's HBr. Now, when you do this type of reaction, generally you have what we call a scavenger. That scavenger will pick up the hydrogen bromide, for example. It could be this molecule here. Pyridine. Sometimes we could use the pyridine as a solvent in this reaction, and as soon as you form the HBr, the pyridine will react with the HBr. Let me remember to turn on the audio. Okay, we just lost the internet very briefly there. Okay, so the pyridine will react with the hydrogen bromide. Okay, to form a pyridinium bromide. The reason for that, if you do not have a scavenger in that reaction, guess what will happen? Hydrogen bromide will react with the amine, because the amine is a very powerful nucleophile. It is also a very powerful base, and therefore you will not get your free amine. So that is why when you do this type of reaction, you generally use pyridine as a solvent. Sometimes you use some other amine as solvent also. Okay, so that is an example of SN2 reaction using ammonia. Now, the one problem with this reaction is, once you form the amine, the primary amine, this primary amine is capable of going back here to react with this alkylating agent to form a secondary amine, and then the process continues. So you really have to control this. It has to be a very controlled process. Okay? Okay, having said that, we could also use this if you want to make a secondary amine. In an SN2 reaction also, okay, here, if you take a primary amine, okay, so the primary amine could do the same thing that the ammonia did. Come here, displace this, and then you have this here. Bromide is here. And so once again, the bromide will simply grab the proton, and you end up with this here. Of course, if you have your scavenger in the reaction mixture, that will pick up the hydrogen bromide, okay? Okay, so in this case, you could use this to make your secondary amine. Now, supposing you want to make a tertiary amine, in that case, you start with a secondary amine. Okay, start with the secondary amine, and then of course what you get, you simply get your tertiary amine. Okay. So this here is for this one here, and this is for this here. Okay, so now, so far I've given you 9 different methods for making different types of amines. So at this point, let us now go to the reactions of amines. Reactions of amines. The amines are capable of reacting as nucleophiles, so I would say nucleophilic. Reactions. Any one of those amines, let's take, for example, a simple amine. Any one of the amines will be capable of reacting with each one of the acid derivatives, carboxylic acid derivatives. Okay. In this case, it will react with each one of them to form an amide. For example, if we take, I believe we've done this several times already, take an acid chloride, react with an amine, and change the color of blue here. Let us use this blue over here. Okay, so this is an example of nucleophilic acyl substitution reaction. I believe we did the mechanism for this when we were dealing with the chemistry of carboxylic acid derivatives. So you form an amide. It will also react with an hydride. Bless you.
Thank you so much.
It will react with any anhydride also to form an amide. In this particular instance here, we are also losing HCl. Okay. Here we could also form the same product. Well, let me do it separately. Essentially, in this case, we form the same product, but let me use a different anhydride so that it doesn't look like the same product. you use propanoic anhydride, okay, in that case you now get this. You still get a secondary amide. Okay, use the same color here. Okay, it will also react with an ester. Okay, react with an ester. Keep in mind we have basically the three carboxylic derivatives that we discussed earlier. You have the acid chloride, you have the ester, and then you have the anhydride. Okay, it will also react with the ester. For example, it could react with this here. Okay, these are all examples of nucleophilic acyl substitution reaction, if you recall. And then what you get this here. Also we form of course, if you start with a secondary amine, in this case, for each one of these cases, you will get a secondary, you will get a tertiary amide. Okay. If you start with a primary amine, you get in all of these cases here. These are all secondary amide. But if you start with a secondary amine, then you are going to get a tertiary amide. Okay. For example. Say I take the methyl benzoate and I react with a secondary amide. I'm sorry, secondary amine. And I will obtain this product here. And this is a tertiary amide. Okay, one very useful reaction that produce a very a widely used drug uses this particular reaction methodology. For example, if you take this molecule here, just to show you, even though these reactions are very simple reactions, they do sometimes produce very important pharmaceutical drugs. If you take this primary amine and you react this with acetic anhydride, you react with acetic anhydride, you get this drug here. And this is another case of nucleophilic acyl substitution reaction. Does anybody know the name of that commercial name for that compound? Okay, this is Tylenol. Okay, I'm sure all of you have used Tylenol before. Very simple molecule, but these guys make a lot of money out of it, right? Okay, and in different countries they call it a different name. In I believe in different parts of Europe and Africa they call it paracetamol, and different parts of the world they just the same chemical they give it a different name. So anyway, so all you are doing here is using a simple nucleophilic acid substitution reaction between an amine and in this case an anhydride to form your product. You could also get the same product if you use acetic chloride. But the industry uses this is the process they use because this is a much cheaper starting material than the acid chloride. Okay, and plus the acid chloride is a lot more difficult to use. So anyway, so just want to let you know that this is something that has some commercial value. Yes. How come the name is different? Huh? How come you say that again? Say that?
She's talking about the actual taste of Tylenol, like how they use how it's formed.
Why do they give it different name?
No, when you eat it, how your tongue interprets it.
Oh, your tongue. Well, I'm not an expert on that. Oh, okay, I see. Okay, I got you. Okay, now what happens, those formulations they give you, there are some other additives in there, fillers. They use, now that tablet that you get is not all Tylenol. It's not all, actually the name for this is acetaminophen. That is the chemical name. Acetaminophen. That is what we chemists will call it.
I mean, well, yeah, that is,
Okay, acetaminophen. So, but yeah, to answer your question, the reason why it tastes different in your mouth is because of the different, different fillers they use. Okay, not that tablet doesn't all contain the Tylenol. Okay.
Okay. Well, isn't there a difference between like Tylenol and then like acetaminophen? Because like
no, but acetaminophen is just the name. Period. Yeah. That's just the name. Tylenol is a trade name.
Okay.
Yeah. Paracetamol is a trade name. Now if you make your own drug, you call it whatever you want.
Exactly.
You call it Cinda if you want,
No, that's what I'm doing.
But the acetaminophen is just the chemical name. Okay. Anyway. Okay, so giving you examples of reactions of amines reacting as a nucleophilic agent. Okay. Now let us also, in that vein, give you a related reaction called this Hoffman elimination. Hoffman was a very active chemist in those days. Hoffman elimination. Now what this is, if you take this molecule here, let's also say we take this. Remember we told you that we could use the ammonia or the amine as a nucleophilic agent. say you take ammonia and you obtain this. If you obtain that, okay, this is just a straight SN2 reaction between ammonia and this here. You obtain this. Ordinarily, if you have this type of molecule, oh, I have to just use this here, okay. And you want to form a carbon-carbon double bond, you want to form an alkene. What we normally do, take the alkyl, in this case an alkyl bromide, you react with hydroxide with heat, and you get what we call an E2 reaction, which is an elimination reaction. Now, when you do this, you expect to obtain the major product will be that is more substituted. The more substituted product will be the major product. In which case, you expect the alkene to be formed. Let us say this is carbon 1, 2, 3, 4, and 5. So you will expect the alkene to be, the double bond to be formed between carbon 2 and 3, because that will give you the more substituted product. Okay, and that follows what we call the Z-self rule, which says that anytime you are forming a carbon-carbon double bond, the more substituted alkene will be formed. In this case, we will expect to get this as the major product. That's what we expect to get for the major product. And the minor product, of course, will be this one here, if you form the carbon-carbon double bond here. So this is the minor product, okay? Now, but if on the other hand, what you want to do is to obtain the less stable product as the major product, then you use this procedure that we refer to as the Hoffman elimination reaction. Take this out of here. To do that, this is what to do. You take methyl, you have your amino group right here. You take methyl iodide, take an excess of it. An excess of methyl iodide, of course, you know that this amine here will be displacing the iodine to form the first thing it will do to form a secondary amine, then to form a tertiary amine, and finally a quaternary amine. So you are going to form this here. So you are going to form a quaternary amine with the iodide simply acting as a counter ion. That is what you form. with the excess of this. Now, if you now introduce silver oxide in water, what the silver oxide will do to produce hydroxide, silver oxide reacts with the water to produce hydroxide, and that hydroxide will displace the iodide here. So you get this intermediate. Oh, sorry. There is something missing here. So you get this intermediate. So instead of the iodide now, what we have here is the hydroxide. So the reaction of silver oxide in water with this quaternary ammonium compound here what it does is to exchange the iodide for hydroxide. And then at this point, that hydroxide will simply now come in, we'll pull out one of these hydrogen here. In essence, we are going to form the less stable alkene product as the major product. Okay, so notice here, this carbon here now is this here, and this carbon here is this. What is happening here? I told you this was an E2 reaction mechanism. What is happening? You don't have to give the reaction mechanism, but so that you understand what is really going on here. The hydroxide, in essence, comes here to grab this proton here, and in so doing, the proton leaves a pair of electrons behind, and this is a good leaving group. That's a tertiary amine leaving group, and therefore you form this here. So we call this the Hofmann elimination, and what it does is to allow us to make the less stable alkene product as the major product. Okay, for example, are you writing this? Can I move on? Okay, let me give you one example. Supposing we have this, secondary amine, and then I say,
I have a question.
Yes.
So if we're doing an Hofmann elimination, do you want us to show the amine being attached, or do you want us to show the double bond being made?
Oh, is no, the double bond is, when you do the Hofmann elimination, you are actually forming the double bond. That's what we want to form. Okay, but I went through the different steps just to show you what happened.
Right. So what I'm asking, since it's the reaction of amines, do you want us to show the amine steps, or can we go straight into the double bond? That's what I'm asking.
No, okay, it depends on the kind of question I ask you. Okay, let me finish this one.
Okay.
Supposing I have this. I do this here. SS, right? Okay, that will form the quaternary amine. And then I do this. What does this one, second step, what does it do? What does it do? Replaces the iodide with the hydroxide. And then apply heat. I say, give me the product. Give me the major product. Okay, give me what you think will be the major product. Okay, let me go ahead and number the carbons here. Let us call this carbon 1, 2, 3, 4, 5, and 6. Okay? What do you think the major product? Where will the double bond be? Will it be between 4 and 5, or will it be between 1 and 2? Save some time here. The double bond will be between 1 and 2, because what is going to happen here, when you lose hydrogen here, you are going to displace this. Okay, this will open up. Okay, so therefore, this will be the product. And then the nitrogen is here. That would be the major product. Okay? Okay, how do we get to this? Keep in mind the first thing that happens when you do this here, what do you get? You obtain this. When you use the methyl iodide, of course, with the iodide here. Okay? And then when you add the silver oxide in water, what that does is to replace the iodide with the hydroxide. Well, keep in mind, all I'm giving you here, all I ask you to do here, in this case, I just ask you to give me the final product. Supposing I ask you to give me the product at each of the stages, then you have to do this. Okay, so this is here, and this is here. Now, hydroxide is here. And then finally, when you apply the heat, go to here. Yes. Because what you want to do is to form the less stable alkene product. Because what are the possibilities here? It's either if you remove this hydrogen here, and you form a double bond here, this nitrogen carbon bond will break, and that's how we get to here. On the other hand, if you remove this hydrogen, you form a double bond here, that will be more stable. This will break, and then you get this product. Okay, this is the minor product, and this is the major product. Okay? Okay, so anyway, there is one more major reaction I want to discuss with you before we leave. Since this is the last, since this is the last lecture, so I could borrow about 5–10 minutes from you guys, right? Okay.
We never agreed.
When will I pay you back? Is that what you're asking?
100%.
Okay. Set of reaction number 3. We want to now look at the reactions of aromatic amines Now, if you have the aromatic amine, typically aniline, the amino group is such a strong activating agent if you recall when we did the aromatic compounds, okay, we talked about the electrophilic aromatic substitution reaction. We have the activators and deactivators. The amino group is such a strong activating agent that if you add bromine, bromine will react with the aniline without the use of a catalyst. In this case, bromine in water will give you this. Okay, amino group is an auto-para director to this. Instead of monobromination, you are going to get a tribromination because there is no way you can solve this. Now, if you want to lower the activation for the amino group, what do? You could react with, say, like acetic chloride, or do what we call acetylation. Remember, we told you the amine will react with any of the carboxylic acid derivatives, so you could get this. Okay, so now we have now acetylated the amine. Okay, in other words, we add the acetic group to the amino group. Now this, what we call the acetamino group, this group here, is not as activating as the amino group because of the carbonyl group. The carbonyl group is drawing electron away from the amino group. So therefore, it does not activate the ring as the amino group would do. So in this case, you could now take your bromine, and instead of doing a tribromination, you get your monobromination. Okay, the acetamino group is we call this acetamido group. That is this group right here. Okay, so now you get bromine here, only monobromination. It is a para director because it is such a bulky group, it directs the incoming group to the para position. So at this point, once we've done this, you could now hydrolyze this. Keep in mind, this is an amide, and just like any other carboxylic acid derivative, you could hydrolyze the carboxylic acid derivatives, okay, in a nucleophilic acid substitution reaction, in which the hydroxide will be your nucleophile. Attach this here, this opens up, and then you obtain your free amine. So what have we done here? We use this acetamino group almost as a protecting group, okay? Because this is what the compound we want to make. We want to make a mono-bromo product. If we had done that directly with the amino group, we cannot do it. So therefore, we acetylate the amino group from the acetamino group, and then brominate this compound here, and then hydrolyze from this. Okay? Okay, the last set of reaction I want to give you is a very, very important reaction. You guys will say, why you say the most important reaction to the last minute? Okay, and that is the diazotization reaction. How many of you watched the video from last night? Okay, so the reason I took some time to get there, because we've already done that, because I know that you guys have probably watched this already. So, the last set of reactions before we leave today, diazotization. Of aromatic amines. If I have this, I take nitrous acid. Notice this is nitrous acid, not nitric acid. You could use hydrogen chloride or sulfuric acid. It doesn't really matter. If you do that, you get this here. With the chloride as a counter ion, just right here. So we call it the diazonium salt. Or diazonium ion. Now, this diazonium ion is a very important intermediate. We could take this, react with sodium iodide or potassium iodide. What do we get? Because in essence, what you have here, this is nitrogen. And nitrogen is a very good leaving group. Nitrogen simply just pops out of the system. Okay? And then you could have this. So this is the first method that we know that will introduce an iodine into the benzene molecule. Those of you going to pharmacy, you will find that this is a very useful reaction in making drugs. We could take the diazonium salt, react with copper cyanide in the presence of potassium cyanide. What do we get? We get this. Okay, cyanobenzene, of course, you know what we can do with that. That would take us to all kinds of other products. We could take the diazonium salt, react with copper bromide or copper chloride. we get this here. We could take this, react with silver oxide in water. We replace the diazonium ion with an hydroxy group. We could also take this diazonium ion and react with hypophosphorus acid. Now, what are we going to do? We will replace the diazonium ion with hydrogen. Many of you will say, why do you want to do that? Okay? Okay, I'll give you just one more reaction and that will be the end of today's lecture. So these are all of the reactions. These are all of the reactions of the diazonium ion. Okay? Now, I'll give you one more reaction. Supposing I ask you to, starting from benzene, to give me a synthetic scheme for this product here, for this compound here, starting from benzene. Okay? Just to show you what we can do with the diazonium ion. Okay. The first thing I will do, take a look at what we have here. We have to form a new carbon-carbon bond. And then we see that the bromine, the two bromine are metal to each other and also metal to the methyl group. Ordinarily, that would be very difficult to make because each one of those groups are auto-para-directors. There is no way we can do this without the diazonium ion. So what do? We start off by doing a Friedel-Crafts alkylation. Start with Friedel-Crafts alkylation, then we do a nitration. Okay, you know the reagent that we use for nitration? Now after the nitration, I then reduce the nitro group to the amino group. Okay? I could use any one of those reagents we gave you earlier. Now I have my amino group here. Now, if I now react this here with bromine, the amino group will be the director because it is a stronger director than the methyl group. So it will direct the bromine to this auto position right here. Okay, so bromine, water. Now I have this. Okay, now once I have everything in place, guess what I want to do now? I want to remove the amino group. Okay, how do I do that? I form the diazonium ion, nitric acid in the presence of sulfuric acid. Now I form my diazonium ion. Now once you form your diazonium ion, then I simply now react that with a hypophosphorus acid. I will replace the diazonium ion, and therefore I go to my product. Okay, so we have come to the end of today's lecture. I want to thank you guys for giving me your extra 15 minutes. Okay, so enjoy the rest of your evening. And what I will do, I will try to post this material before I leave my office today. So for those of you who are seniors, I will see you tomorrow, and the rest of you, I will see you on Thursday.
Can we push it back? Give me
like
just give me this 400.
H2CO3 or H3PO2?
H3PO2.
Which one? A2? You say H2CO2?
H3PO2.